Welcome. This is a video presentation of the paper, The Origin of Matter and Gravity, What They Are and Why They Exist. Part 1, The Ideal Particle. We're going to start by looking at the radius of the small energy quantum. We saw or argued in the paper on the geometric mean expansion of space that expansion produces two quantum levels. One of them, based on the energy of the observable universe, is the small energy quantum, or SEQ. And we'll show it by equation form here, E sub SEQ. We calculate that by taking the square of the initial energy, which is the Planck energy divided by 2, and dividing it by the energy of the observable universe. And we get C times h bar divided by R sub h. The objective is to calculate the radius of the small energy quantum. And we'll do it by taking the energy of the observable universe and dividing it by the energy we just calculated for the small energy quantum. And it comes to what we called the large number. R sub h, the radius of the hyperverse, divided by 2 Planck lengths, quantity squared. Remember that E sub O here is c to the 4th times R sub h divided by 4g. And when we divide it by the energy of the small energy quantum, C times h bar over R sub h, we get this number. We'll take the volume of the observable universe and divide it by the number of small energy quanta within it, and we get 2 pi squared times the radius of the hyperverse cubed divided by that large number. And what we want is the radius, and this is the radius cubed, so we'll take the cube root of that, and we get the cube root of R sub h times 4 times the Planck length squared. So that's our radius of the small energy quantum. The radius of the small energy quantum comes to approximately 6.495 times 10 to the minus 15 meters. And our value for the radius of the small energy quantum is very close to the Compton radius, the reduced Compton wavelength, of elementary particles and nucleons. The electron, for example, Compton radius is about 2.4 times 10 to the minus 12 meters. The proton's Compton radius is about 1.32 times 10 to the minus 15 meters. Now, if we take the geometric mean of the Compton radii for all 12 quarks and leptons of all 3 families, we get approximately 1.156 times 10 to the minus 14 meters. We have that here, and if we divide it by our radius for the small energy quantum, we're off by a factor of about 1.78. It's off by less than a factor of 2 compared to the SEQ radius. They're very close. Now, the Compton radius is not the radius of the elementary particle it is associated with. And from Wikipedia, let's get this clear, the Compton wavelength of a particle is equivalent to the wavelength of a photon, whose energy is the same as the rest mass energy of the particle. It's not the radius of the particle, it's the radius of the photon connected with that particle. The Compton radius cannot be the particle radius. It gives a nonsensical relationship in which the larger the mass is, the smaller is its radius. As an example, let's consider the Compton radius of the mass of the observable universe. The Compton radius equation is h bar divided by the mass times the speed of light. And when we insert the mass of the observable universe here, we get 4 times the Planck length squared divided by the radius of the hyperverse. And as we saw in the paper on the geometric mean expansion of space, that's our small radius. That's 3.98 times 10 to the minus 96th meters. So we have a huge mass, and we have an extremely small radius. Clearly, this is not the radius of this mass. Using the example from the previous slide, we find that the geometric mean counterpart of the Compton radius is the correct radius. We can take our value of r sub s in a geometric mean relationship and multiply it by what would be the largest radius, and that would be equal to the initial radius squared. A characteristic we saw in the geometric mean paper. And when we calculate it, we get what we would expect, which is the radius of the hyperverse as the radius associated with the mass of the observable universe. So we're going to make the claim that it's not the Compton radius that's the particle radius, but it's the geometric mean counterpart of the SEQ radius that is the particle radius. And we just saw that it was the geometric mean counterpart of the Compton radius of the mass of the universe that was the correct radius for the observable universe. And it makes sense logically. We find that the larger the mass, the larger the radius. We can take the Compton relation, h bar divided by the mass of the object times the speed of light, and that would equal to lambda bar, which is the Compton radius. And we're going to make the claim that the Compton radius times the geometric mean counterpart of the Compton radius is equal to the initial radius squared. So we'll divide both sides here by the geometric mean counterpart of the Compton radius, substitute in our h bar over mc equals this value here, and work it around a little bit, and we find that the Compton geometric mean counterpart of the Compton radius is equal to 4 times g divided by c squared times the mass. And rearranging, we find that the mass is equal to the geometric mean counterpart of the Compton radius times the speed of light squared divided by 4g. And for example, in our case of the mass of the observable universe, we have r sub h times c squared divided by 4g. And this is the equation that we use for the mass of the observable universe. And we have a direct connection between the radius, hyperverse radius, and the mass of the observable universe. And in continuing our argument that it's the geometric mean counterpart of the Compton radius, that is the particle radius, we find that we get the correct mass to radius ratio when we use the geometric mean counterpart. And let's look at this mass to radius ratio. And we'll start here. The initial mass to the initial radius. The initial mass is a Planck mass divided by 2, and divide that by the initial radius, 2 Planck lengths, and we get c squared divided by 4g. For the observable universe, the mass of the observable universe, divided by the radius of the hyperverse, and the ratio is also c squared divided by 4g. Now we're looking ahead a little bit, not far, we'll be there shortly, but if we take the ratio of the mass that we're in claim of, that's the particle mass, divide by what we claim is the particle radius, and take the ratio of the two, we also get c squared divided by 4g. Let's look at one more argument supporting the idea that it's the geometric mean counterpart of the SEQ radius, or the Compton radius, that's the particle radius. And this deals with the Schwarzschild radius of a particle. And as a bit of a reminder, we talked about this in the first paper in particular, the radius of a hyperverse, this being the hyperverse here, the surface, this is the universe, it's expanding, the hyperverse is expanding at 2c. But at 1/2 the radius, the expansion is c. So let's ask, at what distance from the hypercenter of a particle will the escape velocity equal the speed of light? That is, what is this version of the Schwarzschild radius for a particle? This is certainly an unusual way of using this equation, but this is the equation for the escape velocity. Now, if we put in the mass of the observable universe and 1/2 of the hyperverse radius, because we know where this is going from what we just saw, and work it out, we find that the escape velocity equation gives us the speed of light. And even though there's nothing there and you can't escape from it, and it's not real use for it, this equation works very well in telling us what the expansion speed is, at least, at 1/2 of the radius. So let's start here. We know the escape velocity equation is a square root of 2 times g times the mass divided by the distance. We want the escape velocity to equal c. So we set those two equal, square each side, rearrange, and we find the distance would equal 2 times g times m divided by c squared. Now we'll take that equation and we're going to insert the value that we will claim as the particle mass. So we get 2g times what we claim as the particle mass divided by c squared. And the result is this value here, which is the geometric mean counterpart of the Compton radius. This is the value we claim is the radius of a particle. So it's 1/2 that radius. It matches what we saw for the observable universe, for example. So recall that the Schwarzschild radius of the observable universe is 1/2 the hyperverse radius. We haven't looked at it here, but the Schwarzschild radius of the initial state was 1/2 the initial radius, 1 Planck length. And we have the same situation here, as the Schwarzschild radius of a particle is 1/2 the particle radius. This preserves the initial condition. And so something that's going to pop up to be pretty important very shortly. Let us now move from particle radius to the concept of the ideal number of particles in the observable universe. To roughly calculate the number of particles in the observable universe, we can take our value for the mass of the observable universe and divide it by the mass of a proton. So our equation for the mass of the observable universe gives us about 8.8 times 10 to the 52 kilograms. And we'll place that here and we'll divide it by the mass of a proton. So that if everything in the universe, all mass, was a proton, we'd have about 5.28 times 10 to the 79 protons. Now there are 3 quarks in every proton, and we'll assign 1 electron per proton. So we can take our number of protons, 5.28 times 10 to the 79, and multiply it by 4 to get the number of particles associated with this, and we get about 2 times 10 to the 80th. If we take the arithmetic mean of the masses of the electron, the up quark and down quark, and divide that into the mass of the observable universe, we get about 9.586 times 10 to the 81 particles. If we count the neutrino into the mix, divide the mass of the observable universe by the arithmetic mean of all 4 particles, we get about 1.278 times 10 to the 82 particles. And instead of the arithmetic mean, we can use a geometric mean. And this case here is the observable universe divided by the geometric mean of the electron up and down quark, and we get about 1.68 times 10 to the 82 particles. And if we take the geometric mean, including the neutrino, we get a large number, about 5.7 times 10 to the 83. So we can see there's a big similarity in these numbers. They're all approximately around 10 to the 81, 1082, 10 to the 83rd power. The large number of the universe, our radius of the hyperverse divided by 2 Planck lengths squared, is approximately 6.59 times 10 to the 121st power. Our rough estimates of the number of particles in the observable universe is close to the square of the cube root of the large number. So if we take r sub h divided by 2lp and raise it to the 4/3 power, we get 1.6 times 10 to the 81. Very similar to our number of particles. Now we're jumping ahead a bit. It'll be supported quite well as we go. But we will assume that this is not a coincidence. And we're going to call this the particle number. This value here, r sub h divided by 2lp raised to the 4/3 power, actually represents the ideal number of particles in the observable universe. Notably, we can generate the particle number by dividing the hyperverse radius by the geometric mean counterpart of the SEQ radius, what we consider to be the particle radius. So we take our radius of the hyperverse and divide it by our particle radius. We plug in our values here, and we get r sub h over 2lp to the 4/3 power, which is our particle number. And this is rather analogous to what we have when we take the radius of the hyperverse and we divide it up by the length of a small energy quantum radius. So if we take r sub h divided by the small energy quantum radius, we get the large number, r sub h over 2lp squared, which is the number of SEQ. Let's now look at the particle mass. If we divide the mass of the observable universe by the number of particles, our ideal particle number, we get the particle mass. So here we have the mass of the observable universe divided by our ideal particle number, and we get a mass value, which we will most frequently express as this such here. And you work it out, and the mass of the particle, the ideal particle mass, comes to about 5.4 times 10 to the minus 29 kilograms. Now our ideal particle mass, which is approximately 5.4 times 10 to the minus 29 kilograms, is very close to the actual mass of particles. The geometric mean average mass of all 12 elementary particles is approximately 3 times 10 to the minus 29 kilograms. Very close to our ideal particle mass. And as with the radii, the ratio of the mass of the ideal particle to the geometric mean of the elementary particles is less than a factor of 2. It's the same ratio and same factor as we had with the radius. Particle mass can be expressed in several ways. The most common way we have been expressing it is this form here, and we've seen this version. Our third position here, it'll be very important shortly, where we take the mass of a small energy quantum times r sub h over 2lp to the 2/3 power. And particle mass can be expressed in the same way, say, as the mass of the observable universe, but we use the particle radius here instead of the radius of the hyperverse to give m sub o. And it can be expressed in this Planck relation style, where you have h bar over c times the radius of the small energy quantum. So let's look at the ideal particle. The geometric mean expansion model produces quantities that are very close to what we observe for actual particle radius and mass, and the actual number of particles. These quantities are deeply related, and we will claim that their similarity to actual particle radius, mass, and total number of particles is not coincidental, and that these values are the target values the expanding universe strives for. These ideal particle values are, in summary, particle number is r sub h divided by 2 Planck lengths to the 4/3 power. Particle radius given by 16 times the Planck length to the fourth, divided by the radius of the hyperverse to the 1/3 power. Or it can be expressed as the radius of the hyperverse divided by the number of particles. Particle mass, given by this term here, and can be expressed also as the mass of the observable universe divided by this ideal particle number. So a particle possessing the particle mass and the particle radius is the ideal particle. Remember, there is no particle that possesses that particular mass or radius. This is an ideal particle. These are target values, and they're postulated to be altered by the specific charge or spin relationships within the coalesced component vortices, a topic that will be brought up later.